And the last thing we'll look at today will be a problem from the 40s in section 1.4. And this one wants us to use the intermediate value theorem to verify that f of x has a 0 in the given interval. Period 4, if you're watching this and you're in period 4, I forgot to tell you guys this morning because I don't think anyone quite got this far, but we're not going to do this method of bisection stuff, okay? So all I want you to be able to do is to kind of gain a little bit of exposure to the intermediate value theorem, using it to verify that the function that we're looking at has a 0 on the interval that's specified. So I have the intermediate value theorem copied from the book here onto this page. 42 is the one I'll take a look at with you guys. We have this cubic graph, and you should realize right away that a cubic graph, a polynomial, is not going to have any holes, jumps, or asymptotes. It's going to be continuous. What we want to do is we want to show that this cubic function here has a 0 on the interval from 2 to 3, and we want to use the intermediate value theorem to do so. So remember what the intermediate value theorem said. The intermediate value theorem said if you have a function defined on the interval from a to b that is continuous, and you know f of a is some value here and f of b is some value here, so this would be my f of a value, and then way up here I'd have my f of b value. If you pick any value intermediate to these two y values, and our book calls this value w, if you pick w in between a and b, there's absolutely positively no way that you can connect this point to this point with something that's continuous without crossing w. So you must cross w to get from this point to this point with a continuous graph. What we want to use in 42 is the fact that at 2, check out what happens to this function. F of 2 on this graph is what? 2 cubed, which would be 8, minus 4 times 2, which would be minus 8, and then minus 2. So f of 2 is negative 2. If we also compute f of 3, 3 cubed, getting pretty big, but not too big, 27. 3 there would make this a negative 12, so minus 12, and then minus 2 more. So I have 27 minus 12 taking me back to 15, minus 2 more, leaving me at 13. So basically what I've done is I've determined that on the graph of this cubic, without graphing it, I've determined that I have the point 2 comma negative 2 on it, and I have the point 3 comma 13 on it. If I come down below here and I plot these points, and I'm not going to do this too carefully, I just want it to look believable. I want the point 2 comma negative 2, which would take me down here. I want the point 3 comma 13, which would take me way up here. My graph is a cubic graph. Cubic graphs are continuous. There's absolutely positively no way that I can get from this point here to this point here with a continuous graph unless I cross 0 somewhere in between this x value, which is 2, and this x value, which is 3. So I haven't really written it up, but what we've done is we've used the intermediate value theorem to prove or to verify that we have a 0 on the interval 2 to 3. If you find a 0 on your calculator, you might remember having to give a left bound and a right bound before. That's basically, the calculator is basically using the intermediate value theorem to kind of determine whether or not you're telling it the truth. Because if you give it two values that are both positive, it's going to think that there's not guaranteed to be a 0 on that interval. If you give it two values that are negative, it's going to think you're not guaranteeing the existence of a 0 on that interval. So left bound, right bound, whenever you use the 0 feature on a graphing calculator, it's basically the calculator's way of checking to make sure you're not out of your mind, to make sure you are giving it an interval where there will be a 0. We'll talk a little bit more about things like this tomorrow. If you have any questions, feel free to stop in before school.